Okay, it's a few minutes after 2, so we'll go ahead and get started. We'll wait for Rich to get up here, I guess. But so I'm very pleased to introduce Rich Rotunno. I think for virtually everyone in the field of mesoscale meteorology, it hardly needs an introduction. Rich is a senior scientist in M-cubed. He received a PhD in 1976 in geophysical fluid dynamics from Princeton, and he's contributed to a wide range of topics in mesoscale dynamic meteorology, and I'm not going to list all of them here, things like tornadoes, rotating thunderstorms, squall lines, etc. Through a combination of theory and numerical modeling, his work is directed at understanding needed to make progress in the forecasting of mesoscale weather phenomena. He's a recipient of several awards. I won't go through the long list here, but I'll just highlight a few. He received the Lifetime Achievement Award from the Severe Local Storms Research through AMS, the Jewel Charney Award, and the Rosby Medal. And in 2023, he was elected to the National Academy of Science of the United States. And in M-cubed, I believe we're gonna have that celebration here coming up in a few weeks. And with that, I'll turn it over to Rich.
This work appeared in Jazz as a part 2 of a 2-part series. If you're interested in part 1, go back to the recorded M-cubed seminars. I gave a seminar on part 1 back on November 9th, 2017. So, yeah. Yeah, so anyway, this work has been sort of started some 35 years ago, and I'm going to tell you partly the saga of lee-vortices from my point of view. But this work appeared in March 2020, and a lot of you may remember that March 2020 was the time when they declared the pandemic. And I've got a theory. The theory is that the pandemic, or the little-known effects of the pandemic, is that people have lost all interest in lee-vortices, judging from the few citations that I've gotten on this paper. So it needs to be studied, I'd say. So let me begin the story here. The story is that here's a view from the space shuttle. It's the island of Hawaii, if you don't recognize it. And the trade winds are coming in there from the east. And you see the low-level clouds associated with the trade inversion, and then a big clearing behind the island. And it appears to be, to the eye, a pair of vortices. Now, if you don't believe your eyes, don't believe the flow visualization, a field experiment was carried out. And this verifies what your eyes kind of lead you to believe, that there's a pair of lee-vortices on the west side of Hawaii. Now, some 35 years ago, Peter Smolakevich, Peter, if you're online, I hope you're there. Peter was attempting to do a numerical simulation of the flow around Hawaii. The prevailing idea at the time was that the strong density stratification had a role in restricting the flow to quasi-two-dimensional layers that underwent flow separation off the sides of the island. And so I suggested to Peter at that time, I said, well, okay, the numerical model, we could test that idea. Why don't you set the stress conditions to 0, so that you eliminate the source of flow separation due to viscous flow separation. So we did that, and he came in the next day with this result. He said, well, they didn't go away; they became stronger. And so the question arose, well, vortices need vorticity or source of rotation. Where does that come from? So further analysis revealed that, well, there's obviously in a stratified flow, there's a source of vorticity. And that's comes from the baroclinic generation. Now, if you take a slice right down the center of the obstacle, with the flow coming from the left, flowing to the right, the flow tends to go up as it avoids the mountain and then descends down behind the mountain. And the cool air, the relatively cool air that rises up has an opposing tendency. Gravity tends to make it come down again. And that's the baroclinic effect, is to generate these vorticity. Then there's vorticity that runs into the page here and then comes out of the page behind the obstacle. Now, if you take a bird's eye view from the rear looking upstream, here's the bird, he's upstream. Now, if the bird could see a vortex line, you would see these red arrows going across like this. And then the action of the flow on the middle, if you take your right hand and you put it through the vortex line and tilt down, and you'll see that that would produce a pair of vortices, a vorticity distribution that happens to match the what you observe. We also noted in this paper that for most of the flow, you could interpret this in terms of the conservation of potential vorticity. Now, the potential vorticity upstream is 0 because omega is 0 upstream by design. And there's, by design, there's no surface friction, so there's no sources at the surface either. So, yeah, so what you see here on this complicated figure is looking down from above, the obstacle in the middle, and is an isentropic surface that has vortex lines contoured on it. The solid lines here indicate an elevated isentrope, and the dashed lines behind signify a depressed isentrope. And these vortex lines, they're running. I put in these little arrows to help you see which way they run. They run around the obstacle like this, and these vortex lines are like this. And you can see they go down into the trench here and come up out of the trench there. So they're tilting down on one side and tilting up on the other side, as predicted by the simple calculations. So we're kind of happy about that. But then we had a comment published on our paper by Ron Smith. And he said, well, no. He said the potential vorticity is not 0 in these little spots here. And that fact, not the existence of vertical vorticity, is the salient point. Now, for those of you who don't know what salient means, it means the most important point. It means we missed the most important point. So we went back and sort of, well, let's think about the most important points. What's most important? So shortly afterward, next year, we published a paper showing the time evolution of the flow leading to this flow here. And of course, that's in black and white contours, but since then, this is a paper by Craig Epifanio and myself, where he had this very nice graphical images. So what you're seeing here is the isentropic surface, and we're looking at the flow as it goes into motion. So we put the obstacle into motion, or you can think of it as the fluid going into motion with respect to the obstacle. The dark lines here, the dark area shows the upward displacement of the isentrope, and the reddish lines show the downward displacement of the isentrope. And what I'd like you to pay attention to here is that the fact that the vortex lines on the isentrope remain on the isentrope as the lee vortex develops. Now, they remain on the isentrope. Remember, omega dot del theta means that the vortex lines lie in the isentrope. So omega dot del theta equals 0 means that there's 0 potential vorticity. And so what we established with this is that, okay, well, it appears that the flow and the vorticity it produce a vortex. But that vortex induces a motion that brings the cool air back around on itself. Once the cool air makes reconnects with itself, then all the vortex lines are captured within the vortex, and at that time, potential vorticity is created. So vorticity came first, potential vorticity comes second. So at steady state, all you see is the potential vorticity in the flow. But if you're interested in physics, cause and effect, what comes first generally can cause what comes second. So, our position on this was that, okay, well, the vorticity is still an important thing to think about because it produces the flow that produces the potential vorticity. So, it went on. So I said, okay, we'll give you that one. But what about this one? What about when the isentrope covers the entire obstacle? In this case, we have a braking wave. In the case where there's a braking wave, the hydraulic jump in here, braking wave, and that braking wave induces a force against, the force is against you. So the force is against you and against this U here. It's against you and produces a wake, and that produces the lee vortices. And an example of that, then, is this paper by Christoph Scher and Ron Smith using the shallow water equations, the 3D shallow water equations, showing a flow past an obstacle, a completely submerged obstacle, with a hydraulic jump forming on the lee side. And there it is there. And as the flow goes through the jump, it experiences a loss of energy. It's sort of the classic hydraulic jump where the flow can preserves its momentum and its mass going through the jump, but loses energy. As it loses energy going through the jump, we create in the shallow water system PV, but it's tantamount really to the vorticity, and you have lee vortices, the representation of the wake through this system. So what are the issues? The issues then are the two-layer shallow water equations at steady state. They have dissipation in this type of flow in the braking wave, and PB is non-zero, and that produces lee vortices. That's the position of the shallow water theory. And with the primitive equations, we showed the initial value problem where the isentrope, where the obstacle cuts through the isentrope, and we showed that the sequence of events was that first it was vorticity, and that produces a flow that produces potential vorticity. But what I'd like to do here is kind of do a conflict resolution. I'm doing an intervention, some conflict resolution, and so let's. The idea here is then we're going to meet the shallow water equations on their own territory to simulate those kind of flows that are being attempted to be simulated with shallow water theory using a continuously stratified fluid. So to do that, we're going to analyze the primitive equation solutions applied to a quasi-two-layer fluid at statistically steady state using a direct numerical simulation of the Navier Stokes. So one of the things that need to be looked at is the hydraulic jump. And again, go back to the seminar of 2017 to get a full explanation or a full exposition of the problem here. So this is the shallow water equations, a representation of a hydraulic jump. So here's a single layer of fluid flowing past an obstacle with the conditions of view, mountain height, and inversion height set that there will be a hydraulic jump, a stationary jump in the lee side of the mountain. Now, in the shallow water equations, this is called like a weak solution, because what happens is that the surface, the free surface, tends to become double valued. In other words, this surface here tries to go back on itself and violates all the assumptions of the theory. There can only be one height per location, and you can't have two heights per location. So what the mathematicians do is they fit a shock or a hydraulic jump through here, and this is called a weak solution. So this is basically what we call a parameterization. There's a parameterization of what happens in the space. Now, what really happens in the space, if you kind of look at this magnifying glass, and you see there's actually a motion that covers a fairly wide stretch of territory behind the obstacle. And just to help you visualize that, it's a rolling motion that looks like this. And for those of you who have tried to do a river rafting or tubing down the red, you'll know that when you get to this point here, you have to gather your momentum to get through to the other side. Otherwise, you'll be stuck. You'll be stuck in this eddy. And an example of that is this unfortunate swimmer who finds himself in a hydraulic jump. So the objective then is to show that this rolling motion, this rolling motion, is intimately connected to the lee vortices, and moreover shares the same qualitative dynamics as in a continuously stratified flow. Whereas I'm going to try to explain what really goes on in the shallow water equations, what's being parameterized. So so here it is. Our intention, therefore, is to look at the flow that the shallow water equations attempts to model for a situation in which the leeside hydraulic jump and lee vortices form. And to do that, to dispel any questions concerning the possible artificial effects of parameterized turbulence, we've carried out a DNS for a flow with the Reynolds number high enough to produce turbulent motion, but low enough to respect the rules of the accuracy of direct numerical simulation. So that turns out to be about 5,000. In real atmosphere, it's like 10 to the 8th. But anyway, this is sort of a prototype. So what you're looking at here is the initial condition. There's a flow coming from the west to the east. The green lines are the isotropes that vary strongly through here. This red line here is the mid-isotrope. So there's a layer of constant density with a sharp transition through a layer of another density. So that's like the shallow water equations. But since this is a finite difference model, you have to give it a break and don't stress it out with too strong a gradient. So you put it like that. As I said, these conditions are set so that we expect the hydraulic jump in the lee. And so I'll just give you a preview of what happens. I'm going to, using vapor, we put that little red line into motion. Here's the surface, into motion, the way it breaks, and we form lee vortices. So the initial part, again, is in, wave comes over, forms the vortices, and then there's a more or less continual generation, continually backward breaking and continual evolution of the, and it eventually reaches a statistically steady state. Here's a view now more quantitative, looking at the on the top figure is the flow. You've already seen, you've already been introduced to the green isotropes and the red isotrope, and they're coming down, and the blue and the red here represent the negative and positive vorticity, spanwise vorticity that's, if it's red, it's going into the page, and if it's blue, it's coming out of the page. So there's our vorticity coming out of the page. And here's now a horizontal cross-section through the height of 0.4. And now looking at it down below, you can see that there's this green, the green isotrope is poking down below the level of 0.4. As it pokes down, it produces, it has associated with it these positive vertical vorticity on the right and negative on the left. So what we're going to do then is take the average of this flow over the last hour of simulation, and it shows what your eye kind of indicated, that there's predominantly red. There's a red state on the south and a blue state on the north. So of course, if you take by Kelvin's circulation theorem, if you integrate around the whole box, the average vorticity is 0. So we're going to analyze one side. We can analyze here the red state and the positive vorticity. And so everybody likes to think positive. We'll think positive. So this is what we have here. We can analyze the vorticity equation in flux form. And so it's written like this. Just concentrate on the first equation here. That's the vorticity equation in a flux form. And you'll notice right away that the flux in the vertical direction is 0, as it must be, because the vertical you can't have a flux of a vertical vorticity, or you can't have a flux of vorticity by a vertical flux. You can only do it by horizontal, and by forces applied laterally to the line, like this. So another way of illustrating this is that this equation is essentially the fluid version of the basic physics of applying a torque to a point. So there's a force at some right angle to the vortex line, and that's what changes the vorticity. So you could think of this is basically minus the force in the y direction, and this quantity in parentheses is the force in the x direction. So let's do the analysis then. So at steady state, the first term is 0. D by dt of the time average is 0. Doesn't change over this last hour period. The other thing that we could neglect right away is the direct viscous effects. They don't seem to matter much. And so we're left with analyzing this. So what we're looking at here then is the two flux vectors that go into making up the steady state balance of the vertical vorticity equation. So first thing to deal with is I wonder, well, are the time correlations between these variables important? So we investigated that, and sure enough, well, that's the exact form, and it balances very nicely. I'll show you in a minute. And this is just multiplying the mean variables, and there's hardly any difference. So the time correlations don't really matter. The other thing to notice here is that the x component of this vector here is mainly the u the velocity is u times the vertical vorticity, and so we suspect that this w eta term, this w xi term, is small in this vector. The y component is mainly concentrated along the lee side of the obstacle, which would be here, and and you can see from the figure v is almost 0, and so you suspect that the main contributor then is the w eta term. So in the second approximation, then you can see that there's hardly any change between doing this and this. All right, so what have we demonstrated here? So we've demonstrated, let's see, so this is that's the balance. So if we iterate around the box, then we can find that that the flux out the backside here of vertical vorticity is intimately connected to this flux into the box from north to the south of vertical vorticity, and it has that it's what the Haynes and McIntyre call the non-advective flux. It's not directly transported, but it's a flux vector nonetheless that comes between north to south. And the importance of this result is that it connects at steady state the vertical vorticity directly to what's happening in the horizontal vorticity behind the obstacle, and we already know that W is negative back here, and we saw in the figure that eta is negative. Now, if you're paying attention to the movie, this flow is rock solid in time as it goes, and so to a very good approximation, the equation for the spanwise vorticity can be written like this, where this is the streamwise velocity, this is the variation of eta along the stream, and this is the baroclinic term. So as the flow comes down, it's accumulating this baroclinic vorticity, and since it's coming down just on the inside of this worm tongue, d theta dx is a positive number, u is positive, and the result is negative. So if w is negative coming down, eta is negative coming down, this result is positive. U is positive and zeta is positive. So we've made a strict mathematical connection between the steady state descent of air, baroclinic generation vorticity, and the existence of vertical vorticity exiting the box. For the rest of the path, for this again the eta equation, it's the turbulence kicks in, and something like that, and the balance there is between the mean flow and the eddies. So what this does is extends the pattern downstream. So summary is that this continuous fluid version of the shallow water equations hydraulic jump, given by this figure here, has a backward breaking wave with baroclinic produced spanwise vorticity, given by this formula here. This means that the spanwise flux of vertical vorticity, given by this term minus W eta, is negative, and I'm sorry, it's positive. Duh. Okay, it's positive, and so that this term here, no, it's negative, and then therefore this is positive, and therefore we've connected the rolling motion in the roller behind the hill to the vertical vorticity that's coming out. So, and the role of turbulence is to allow downstream fluxes. And now, before you get ready to fidget and get up and I have epilogues, so don't get too excited. We're not done yet. So, what's the nexus with potential vorticity? So, going back to, here's a theoretical paper by Christoph Scher showing in a continuously stratified flow that irreversible processes here will give rise to a flux of potential vorticity from left to right, and from spanwise flux. And so that J is totally due to irreversible processes. And so if we analyze this this potential vorticity now in the simulations I just presented, here's the J component of the flux, the Y component of this J flux, going from spanwise from north to south, and then here are the two contributions. There's a frictional contribution and a diabatic contribution here, and they both contribute, but the lion's share of the contribution comes from in the zone that explains the total, comes from the it's basically the thermodynamic term. And the thermodynamic term shares with the vorticity analysis the term W eta. And as is, again, well known from the paper by Haynes and McIntyre, potential vorticity inherits most of its properties from the vorticity equation. And just anyway, so yeah, that's a major. So with this, I feel like we've unified views of potential vorticity and vorticity on this problem. To look at more geometrically at the problem, the potential vorticity can be written as the absolute value of vorticity times the variation of potential temperature along the length. So in these problems here, here's the color scale. So if the color goes from light green to blue, then that means that theta is decreasing along the length and has negative potential vorticity. And then vice versa on the other side, if it's going from blue to light green, then the temperature is increasing along the length, and you've got positive. So this is a geometrical view of running some vortex lines through slices of the potential temperature field, and the colors correspond to the colors of origin in the undisturbed flow. Here's another kind of interesting loop found using paper. Here's one that it kind of lassos around the overturning flow on the lee side, and you can see more clearly here that green going to blue, negative, blue going to blue going to green, and positive potential vorticity on those two sides. Getting back to the idea of cause and effect, we see that these lines are set in place even before the wave breaks, before any potential vorticity is created. So here's the flow at 9 minutes, showing the vortex lines. This blue line stays blue, this green line stays green, this green line stays green. So all the there's no potential vorticity yet, but the flow is about to break and capture those lines and create potential vorticity. Again, that beginning part looks like that. So to summarize this epilogue, the nexus with PV is that the original cartoon works surprisingly well to explain the basic distribution of vorticity in a lee-vortex. The role of diffusion is to allow that vorticity to extend downstream and be kind of more locked into the fluid. And so the musing about this comment that if you count today has started a dialogue that's going on 35 years. I thought, this could have all been avoided by changing one word in the sentence, But anyway, that's the other epilogue 2, and this will be short. What about shallow water theory? How do you understand shallow water theory? Where does its vorticity come from in the rolling motion? So let's go back to the hydraulic jump, and you say, okay, well, if you look at the equations, you say there's no baroclinic vorticity term obviously in the equations. So where does it come from? Or even just looking at water wave theory. Now, if you look at water wave theory, the way if you had a course in it, and the way I learned it was that vorticity is 0 beneath the free surface, and then you can match the pressure condition and the kinematic conditions at the free surface. You can derive the surface wave equation and so forth. And you could do actually numerical simulations. But if you haven't guessed by now, the vorticity is hiding in the free surface. It's it's there. Even if the density is 0 above, there's still a gradient of density at the free surface. And this was used by this group, Baker, Mirror, and Orzag, over 40 years ago to simulate water waves. And this is a water wave, and the vortice, the little curling vortices, that's courtesy of me. I put them in based on what I think was happening here. And so, so here we have they didn't carry it all the way through to the wave coming over and touching back on itself, but I took out my Sharpie and I made a prediction of where it would go. But you can see what happens here is that before this happens, the vorticity is 0 everywhere in the gray zone here. So there's no place where you can have a connected line that would have circulation. Okay, but now once this surface comes back and touches itself, you can draw a line, and it'll have vorticity within it, and it'll have circulation. And this is perhaps a more vivid example is this, where underneath the surface feet, the water has 0 vorticity. But once that wave comes along and touches the surface again, then there'll be a braking wave. There'll be a braking, rolling motion that will come in and have vorticity. So with that, I'm at the end here, 34 minutes, and good. Yeah.
Questions?
Hey, Rich, thanks. What do you think would be the takeaway for parameterizations? Like there's, you're showing a lot of, which we already knew some of, but you're elucidating further the structure in turbulent flow, right? And that there is specific areas of transport, momentum transport, and even PV creation. Have you thought about what we should take away from this and like how we're looking at subgrid scale motions across all kinds of scales of simulations, but there's a lot of, even for small scale or large scale, where we're going to have lee-vorteces created and not resolved well.
I would think, I haven't seen any, maybe Branko or you can tell me, I haven't seen anybody who's actually looked at a DNS of a breaking wave and gone back and checked and see how the parameterizations are doing with it. But it's possible. It's possible to do. Yeah, this is mainly about explaining what we think we know in the shallow water equations and how what they're representing in the continuous. The problem with the shallow water system is it's got two discontinuities. It's got the discontinuity of air density, and then the discontinuity that comes out of solving the shallow water equations, which is the height discontinuity with distance. And so everything's kind of wrapped up in that innocuous little thing that you put in and say, okay, we get to continue the solutions. It's a weak solution. The applied mathematicians are happy, and we move on.
So Rich, what happens when you decrease the upwind flow there, or the flow of the shallow
it'll
water system,
eventually,
and it goes subcritical?
Yeah.
So does that?
You could eventually conjure up a situation where the free surface will not go over the hill. It'll be blocked by the mountain, just in 2D. If we can get around, if it's 3D, it'll go around. But, like the first.
And do you get water?
They do, and it's a more complicated shallow water theory that was worked out by Christoph Scherer and Ron Smith, to looking at, they call them flank shocks. Yeah.
Did you look at any cases, or I don't know if you took an interest in simulating cases where it produced a wake with vortex shedding, with alternating vortices forming and shedding? Does that case only arise when the surface drops below the mountaintop and can't get around or can't get over, or what are the particular conditions that produce that?
We didn't do that in this study, but back with Peter, we did studies. We found that we found that having the angle, the long axis of the obstacle tilted with respect to the wind produces alternating sequence of eddies. I don't
But
really-
you would expect that even with a symmetric mountain,
Yeah,
you
you
still
would.
would expect a regime with shedding, I think, wouldn't
Yeah,
you?
you would. You would. No, I think things are just, yeah, we didn't see that. But I think, I think Christoph Scher and Ron Smith did a stability analysis of the shallow water, and they find instabilities. But, yeah, maybe the Reynolds number is too low.
Just to kind of follow up on that question, I don't know if you can go back to the animation where you like started the simulation and then showed the vorticity, but it did look like at the beginning there was like 2 vortices that kind of moved away, and then before you got that steady state set up.
Yep. I know which one you're talking about. This one. Yeah, so we'll go, yeah, I'll go back, and then ready, set, go. Those, right? I don't think I could stop this midstream. I went back to it.
Do you know what's going on there?
Well, yeah, I think that's the what's going on there is, what's going on? What's going there? What's going on there is this, is that, let's see if I can point with this thing. Yeah, so this is that backward breaking wave, and this is the tongue of high theta that's plunging in. And so this high theta that's plunging in, this is associated with this vortex line. You see this is the positive one, so what you're seeing there is the positive vorticity. The red is where this vortex line. Yeah, or this one, yeah. Yeah, there. Well, this is plunging down. This vortex line comes up here, represents the positive vorticity. So what you're seeing there is the tilting of the vorticity produced baroclinically in its purest form. But then it gets messed up by turbulence
But why does it then transport away the vortex?
through the turbulence.
You might also have seen like I guess you'd call it a starting vortex associated with the lower boundary condition, which isn't technically coded correctly. I think it probably, for free slip, you should have a normal component of the stress be 0, but the developer of the code was lazy and put the vertical component of the stress to 0, so someone's got to talk to that guy and get him to fix that code. But if you look carefully, you can see this little blue shading develop immediately at the surface and then go shooting off.
I have a quick question, then we'll go to the question online. So you talked about kind of the central role of baroclinic generation of vorticity. What about the role of clouds and latent heating in this? I have to, of course, ask about clouds. So.
Well, I mean, if you have moist effects, they tend to reduce the effects of they reduce stability. And there's a stratified flow effect. So, yeah, I don't know. I don't know. Yeah, the question here is that was just to, in fact, neither the shallow water equations that I showed nor these primitive equations have any, real viscous drag on the mountain. And so the point is not even to say that it's not important. It's just to say there's another mechanism that hadn't been, as far as I know, hadn't been contemplated in the literature, even on, even in the engineering fluid mechanics of, stratified flow past spheres. The idea that something other than drag on the cylinder was making vortices had not been contemplated.
Okay, we'll go to Andy Heimsfield's question online. Have there been attempts to measure your fluid dynamics model observationally? Maybe he means in a lab or something. He said there may be ways to do it.
There is a lot. There are a lot of lab results, but I think like the experiments I showed in the very second slide, they had measurements, and, the lee vortices are warm. And why should it be warm if it's two-dimensional flow separation? Yeah, the temperature anomalies associated with it.
Do we have any other questions? Otherwise, let's thank Rich one more time.